Okay, it's supposed to be on now.
Oh, can you tell how many people have joined, Paul?
7 at the moment.
Okay.
It's weird actually because it says there's 4 waiting, but it's a bit strange that they're not actually showing it. I'll tell you what, let's just get started. Do you want to do your presentation?
Sure. Hi, everyone. Welcome to the March Sydney Testers Meetup. Today we're having an overview of machine learning for testers by Paul Maxwell-walters. So our agenda tonight is there an introduction by myself, so there's a talk by Paul with 10 minutes of intermission, and we'll be showing some machine learning videos during that time, so people can go to the toilet and get a drink or maybe a snack. Finishing at about 7:15, where there'll be time for Q&A. So so if this is your first time at Sydney Testers, welcome. We're a group of volunteers with a focus to improve testing for Sydney. We organise monthly talks, socials, and other events for Sydney testing community, and we're now been online since COVID, but we're hoping to change that in the next couple of months. So if you've got a venue available, please let us know, reach out. We've had a range of local and international speakers over the last years. Recent speakers include Baz Dijkstra, James Bark, Michael Bolton, Trish Coe, Jean Ann Harrison, Zoe Thevet, Richard Bradshaw, and Rich Rogers. If you want to get involved, speak to us. We love to hear from our local testers about their experience. We'd also like to shout out to our ongoing sponsor, TestDev. All right, Paul, thanks very much. Over to you.
All right, thank you very much. Great introduction, Matt. Thank you. My name's Paul Maxwell-walters, and I'll be doing quite a broad overview tonight of machine learning for testers. So basically, what I'll be doing is I'll be covering the theory of various different types of methods and paradigms they have in machine learning, also a description of what it is. I'll be playing certain videos as well, help to explain certain individual concepts as an overview. Like as I said, it's split up into chunks that are about half an hour each. There's a section in the middle where I'll be playing videos, and that'll be a chance for a brief intermission. I hope the idea of the video of the presentation ultimately is that testers and data scientists or machine learning specialists can have conversations and be on the same page, know what the different things mean, even if testers haven't had direct experience. That's the aim, and I hope it comes out that way. So before I start with the main presentation, I'm going to show you a video about
thank you.
By Google, just describing machine learning used at a very high level.
There have been a number of shifts in the way we think about computing over the past few decades.
The terminology artificial intelligence has come in and out of favor in
the way we think about computing.
Sometimes it's called machine learning.
We tend to call it machine intelligence.
The terminology artificial intelligence has come in and out of favor. It's just the effort to build machines that are better. Sometimes it's called machine learning.
We tend to call it machine intelligence.
Everything was built on logic.
And sometimes it's just
doing
the effort to build machines that are better.
So in the early days, everything was built on logic. But we realized that doing real mathematical were the things that people can do every day.
The real world is actually very messy.
But we realized
hard logical
that
rules
what the real challenges
are not
were
the way
the things that people can do every day.
The real world is actually very messy.
You have to have a system that will learn.
Hard logical rules are not the way to solve really
build machines
interesting
that can
real
learn from
world
their
problems.
environment,
You have to
from mistakes, and from people.
And we're still at the stage where we don't know what is the right path and the right
have a system that
breakthrough.
will learn to get the knowledge.
I mean, there's
You can't just
certainly a
program it all.
whole raft
Artificial
of different
intelligence is an
approaches.
effort to
One of
build
the
machines
subfields
that
we
can
call
learn from
pattern
their environment, from artificial neural network,
And we're still at the stage where we
statistical
don't know
inference,
what is the right
probabilistic
path
machine
and the right
learning,
breakthrough.
Learning, I mean, there's certainly a whole
we're not
raft of
quite
different
sure
approaches
what
to
technique
One of the
is going to
subfields we
lead
call
to
pattern
better
recognition.
systems. And in
Artificial
fact,
neural
probably
network,
not one technique for everything. It's probably a bunch of different techniques and combinations of those techniques.
Any progress we make in building truly intelligent systems is going to depend on progress in technology generally.
And until recently, we didn't have computers that were fast enough or data sets that were big enough to do that.
And so being able to take a particular problem and spread it out over lots and lots of machines is a very important approach because it makes our research faster.
So there's applications of artificial intelligence around us all the time.
When it begins to work, or it does work, it's all of a sudden given another name.
We're all already using it and very comfortable with it.
Things that now we regard as routine, 30 years ago would have been regarded as amazing examples of artificial intelligence.
Anti-lock braking,
Autopilot systems for planes,
Search.
recommendations.
maps,
To decide whether or not this particular email is spam or not spam.
The ability to translate one language to another with your phone. 10 years ago, if you tried to talk to your computer or to your phone, that would just be hopeless.
We're
Yeah, sorry about that. The video was playing. It seems the audio was coming through twice for some reason. I apologize for that. I'll see if I can fix it for the next video. If not, then I'll turn the sound off entirely and just put text up. But I'll carry on. Apologies for that. The question I want to first pose is, what is machine learning? And the textbook definition of it is the use and development of computer systems that are able to learn and adapt without following explicit instructions by using algorithms, statistical models to draw inferences from patterns in data. Now, just to point out that machine learning and AI are sometimes thought of as the same thing. They're not actually. AI is much broader. It includes things like expert systems, agents that are not considered part of machine learning. Also, machine learning includes certain tools such as various statistical tools which are not considered AI as such. Just want to clarify that. Move on. So let me just expand my screen again. This is the agenda for tonight. We're talking about the history and types of machine learning. A pipeline, so the machine learning pipeline from when you first receive data, when you clean it, extract the features you want, model it, you test against historic data, and then send that in the pipeline to production. Regression, we talk about linear and non-linear least squares. We also have a section on clustering, which is I added later, which is on k-means clustering. On classification, we have decision trees, ensemble methods, K-nearest neighbor, logistic regression. Around the time of logistic regression, that's where we have our intermission. Neural networks and deep learning will come next. Evaluating models, bias and variance, about how you test models to make sure that they're accurate and they're sufficient, for your particular use. So machine learning is old. It dates about 200 years. Well, the precursors of it date about 200 years. So Adrien-Marie Legendre develops the least squared method, and that's the start of linear regression. Even before then, George Bayes came up with Bayes' theorem, which is a probabilistic machine learning tool, which is used in machine learning still for things like determining, what emails are spam. First neural network machine was created in 1951. That was an earlier version, not the same as that. It doesn't have a much resemblance to machine learning neural networks that we have now. KNearest Neighbor was developed in 1951. The perceptron, which is the basis for all modern neural networks, came about in 1957 by Rosenblatt. I'll be talking about that later. Back propagation, convolutional neural networks, which are very, very important in image recognition. And then 1997 is when machine learning algorithms and AI starts to really beat humans at their own game. IBM Deep Blue beats Garry Kasparov at chess. Google Brain determines a neural network to detect cats in unlabeled YouTube images. And then AlphaGo beats a human player at Go for the first time. In fact, a human has only ever beaten AlphaGo once in its history of 79 matches. So when it comes to Go, AI completely dominates. So we have certain terms in machine learning. First one is called supervised learning. And that's where the computer's given specific inputs and outputs that are known, and they try and find relationships between the inputs and outputs. So the outputs have already been classified, or you already know what the answer is going to be. Unsupervised learning is you have a set of inputs and no labeled outputs, and the computer has to come up with its own relationships and cluster the data in some way. Reinforcement learning is somewhere between the two. So a computer reacts to the dynamic environment, has a certain goal, but it doesn't have outputs as such. It has, every time it does something right, it gets given a reward, and it has to maximize that that reward as feedback. Other terms, we have models. Models are used, or how we describe the things that we do to make predictions or classifications in machine learning. And they usually weights and parameters, often stored in some file. They represent an assumption about the relationship between input and output data, but then you have to optimize it. And that's called training. So you compare the model to the output, and then you change your weights and parameters until the model produces an output that reflects real life or reflects your test data. And a feature we'll be using that word at length. It's used quite a bit in the industry, in the field, and it's just some variable that's defined in your input data that you may or may not want to model with. So it's size, color, age, that sort of thing. So there are different types of machine learning. You can classify them broadly into 3 different types. The first one is called classification, and that's where you have a set of data that is labeled into different types, and you may expect data in the future. You want to know which type it is. So you have animals, you may have to classify it into dogs, cats, rabbits. And so the space of classification, and this looks like KNearest Neighbor looks like this. So everything on this side is classified as orange, everything on this side is supposedly classified as blue, and this is some space of features. Regression, this comes from statistics, and this is estimating a relationship between an input variable and an output variable. So if you're X and Y on a graph and a curve, you fit the point, is it a straight line? Is it a curve? But either way, the gradient of the curve or the points on the line are supposed to reflect the actual values that are correct. Oh, sorry, your estimation of what the output should be. So clustering, this is unsupervised learning, and this groups items into groups with similar properties, usually called clusters. And but there's no labeled data to check against. It's just you do it to find these relationships. So this is a broad sweep of machine learning algorithms. We certainly won't be covering all of them. We're not. Typical ones, things like decision trees, support vector machines we won't be talking about at all, random forests, neural networks, which there's a considerable about we'll be talking about, boosting trees, which are related to decision trees, linear regression. So you have a whole set of clustering algorithms, which are k-means, classification ones where you have labeled data, regression where you have labeled outputs and you want to predict some future some future value, say if you're plotting values on a graph or something like that. And dimensionality reduction, which is you have a lot of features, you want to reduce it to a small number of features that easy to manage. And there are different very mathematical tools for doing that. Principal component analysis, singular value decomposition. They're a bit too mathematical for me to cover here today. So this is a typical sort of machine learning pipeline, or at least an abstract version of it. You have some data set in a database or through an API or something. You retrieve it. The data might have gaps or something. So you need to wrangle it. You need to fill the gaps or get rid of the data with the gaps. The data may not be normalized correctly, or there might be errors and you have to fix it. And then only then can you get to what's called feature extraction, where you decide the features that you want to model, the features that most correlate with the output that you're looking for, and then you select them and you scale them. You put them into your model. You do this training with some machine learning algorithm. You evaluate and you tune it, and then you might have to go through this step a bunch of times until you have a model that you're happy with, and then you deploy it to production through some various. Often it's done through some ML ops pipeline, which has become more and more common these days, but still very much in the early stages of adoption. So let's talk about the first one. We'll talk about regression. So let's consider XY chart, two-dimensional, y equals a plus bx, where alpha plus beta x, where beta is the gradient of the line and alpha is where it intersects the y-axis. Now, because this is not perfect data, we have to use an error term. And what we want to do is we want, as you can see here, and for every point in this range I, you can define an input and an output and an error. So you find an optimum gradient beta and the y-axis intercept such that the error is a minimum. So in this case, you want to sum all of the errors, which is y minus alpha plus beta x squared, because it's a mean squared error. And then you want to reduce that. Sorry. So how do you solve this? There's a bit of maths here. I'm trying to keep it as low as possible, so I'm not swamping you with maths. But alpha here is the medium point at which it crosses the y-axis. Y is the is the mean point. Y is the mean output, and beta is a vector that describes the mean gradient of this line, and this is the mean value of the inputs x. And then you come up with this equation here, which you use to determine the gradient. And then if you determine the gradient, you can determine the intercept alpha, and then you've got your equation that determines the best fit of this line where it cuts through all these points. So let me just show you an example of this being completed. Here we go. Here, what I've done is let me just move on to the next line, because it actually has the original value. The next slide, because that has the original values. That's the chart of all these height and mass values, but without a trend line going through it. The particular example, which I stole from Wikipedia for this, claimed that it could be modeled as a slight curve or as a line. In any case, I'll show you results from both. So here, if I just go back a slide, you have the mean of x, which I've calculated here, which is this value here. The mean of y, which is this value here. And we work out this, which is for each value of x, you take away the mean of x. And you do the same for mean of y. And then you calculate this sum together, and then you sum it. So you calculate the sum of all the deviations of x minus the mean squared. And then you do the same for x minus x squared, y minus y squared. And this relates to sample standard deviations. And so the idea is to find the exact gradient and the exact y-intercept that is the best fit for all of these points, in the other graph. This is known as the R-squared value. So it's essentially or the sample correlation coefficient. And the closer it gets to 1, the better. The more correlated it is. And so these are the results which I've shown here. And I'll show you the results. So this is the slide from Wikipedia that contains the results. This is for another example where they've changed one of the values to show the effect of variance, but this is what we're looking at. This is a value from Wikipedia, and this corresponds to a beta of 61.272 and an alpha of minus 39.062. So we match the equation for these points. And so this describes the best fit, linear fit of the points on this graph. in terms of x being height versus y being weight. So you can also model this by curve. In this case, you have to take an additional term for height squared because it's a polynomial curve of type 2. And I've taken the value from Wikipedia of a computer calculation of the various parameters. And this B1, B2, B3 in this equation defines a curve that fits all these points, as exactly as possible. And it has quite a high R squared of 0.9989, which is, nearly 1. So there's a very high correlation. Let's move on to the next one. It's clustering. This is pretty easy to explain. So you have a set of clusters of data points, but none of them are labeled into categories. Now, this happens a lot in computer science, astronomy, in image recognition. There's various examples on the website Kaggle about it. Now, so what you do is you define a number k clusters. So you think, oh, this data could be described in 3 clusters. And you drop your clusters randomly, arbitrarily into the space defined by your data set. And every time you do that, you determine the cluster that has the center of the nearest cluster, the mean center of it, and you move and this defines what's known as a Voronoi diagram. So each of these is an equidistant point between clusters, or between these points that you've created. And what you do is you iterate the process. So you redefine the cluster and you move these are called centroids. You move your points to the center of them, and then you repeat that until you reach some sort of convergence, until until the difference in the mean that you calculate in the next iteration is so small that you can't move. And this is how it looks in practice. So this is known as a mouse data set, and it's a common data set to use and to demonstrate k-means clustering. And what you have is that these are your centroids, and they progressively move to the center of the nearest cluster. And in doing so, they change the division between clusters each time. So in doing so, points that were thought as part of one cluster, they become part of the other, because the cluster gets redefined and its mean position gets recalculated. And then you end up with different clusters for each of the years. Obviously, there's some overlap between parts of Mickey Mouse's head, but then it converges to the one for each ear and one for the main face, if you will. So that's how k-means clustering works. The next one we'll talk about is called classification. Sorry. So there are different techniques for doing classification. Possibly the most intuitive one is called decision trees. So what you have is you have some data set, some table with a load of inputs that are categories that can be categorized, and then you have a wait time. So here is, do you have to wait if you fit these parameters? If you're one of these examples, are you likely to have to wait to be served or not? So let's say, for example, you want to make a tree where the stump or the root is what's known as patrons. If there's some patrons there, if it's full, or if there aren't any. So this is the start of that. If you can have a look here, if you look at patrons and you look at all the records where some is selected, they all have to wait based on the historic data. So that is the end of this node. It can't progress any further. You can't split this up. Same for none. So if you have 2 that are none, but they both require but they both have the same output, which is you don't have to wait, then that is a leaf. You can't expand this any further. But if for for full, you may or may not have to wait. So there are wait output values where you either wait true or you wait false, and you can split this up by other parameters in this table depending on if wait is true, wait is false. Now, how do you do that? The idea is to select attributes or features where the categorized output is one or the other, but not both. So here, this is particularly good because at least for none, everybody who is in that data set who didn't who was there when nobody was there got served immediately. They didn't have to wait. Now for some, everybody had to wait, and for full, surprisingly, some had to wait and some didn't. And however, for type, this is French, Italian, Thai burger restaurants. One person had to wait and one person didn't. So this has to be split up further. So this is considered more informative and more orderly. And this is deemed to have higher entropy because high entropy is sort of a lack of order. And the idea is you want your decision trees to be as small as possible. So you want your entropy to reduce at every step. And if you split by patrons here, and if you follow these, you have a lower entropy throughout. That becomes the smallest tree you can have with that data set. And there are different techniques for working this out. So decision trees are intuitive and they're easy to follow, but they're more useful en masse. So lots of random trees, they form forests, and these provide very highly accurate results. And these are called ensemble methods. There are different ones. They don't all apply just to trees. They can apply to other machine learning methods as well. So if the first one's called bagging, and you train with a random subset of the training set. So you take some of the training set and then you train your model with it, select it at random, and then you aggregate them all up. There's another one called boosting, where if you have some poor models, i.e. trees that either overfit, they're either don't produce the right results, or they're too small, or they can be summed up or reweighted so that they go back into training again and they form stronger models, and this is called adder boosting. And there's a very common technique that people use is something called random forests. And if you ever do machine learning competitions, you'll find a lot of people winning with random forests. So random forests create loads of random decision trees from randomly selected sets of features, and some of them will work. So it's very much a wisdom of the crowds, getting lucky approach, if you will. Now, it's not easy to interpret at all. But its performance is very, very good, and for that reason, it's very popular. Now, another technique I'd like to talk about is called the KNearest Neighbor. Sorry, this is the slide. Sorry. And what you do is for a data point, you take the nearest k item. So k is some number that you determine. So you might start off with k equals 1. So k equals 1. If that's your point and you want the nearest one item, it's this one here. So that point now becomes red triangle. If you say that you want k be equal to 3, which is what this is about, then it's still a red triangle because there's 2 red triangles and 1 blue square. But if you want k equals 5, then you have 3 blue squares and 2 red triangles. So this is now a blue square. And then you do this for all the data you want to classify. And this describes what I've shown you. K equals 1, you get a red triangle. K equals 3, you get another red triangle. K equals 5, it gets assigned to blue square. And this is how it looks for large numbers of points. So for k equals 1, it results in lots of noise because you have lots of gaps in between where the other input value or feature value might actually be red, but it's surrounded by blues or something like that. Now, as the K becomes larger, it smooths out, but then in doing so, you may end up with a model that may not necessarily match enough of your data points, and actually have a higher error. So we group these points by category. These have equidistant points between them, and these are the boundaries of what's known as Voronoi cells. This is something that comes out as well in clustering. But these boundaries here are called decision boundaries. So if you have a point like this, which separates a blue classified cluster, a blue classified point from a red classified point, this is the decision boundary. If you find another point and it sits there, it's red. If you find a point and it sits there, it's blue. Depending on the numbers of Ks that you've selected. In half of this talk. No, I'm not playing this again. Perceptrons and neural networks. The neural networks and deep learning are very much the direction where machine learning is going. It has been for at least a bit, and I've devoted it's also quite complex and very interesting. So I decided to devote the second half of the talk to this, and also to checking and validating results. So we have to go back to logistic regression to talk about it. But I'm talking about a type of regression which is actually used for classification. This is called logistic regression. And what makes this difference is it takes a function, or it uses, instead of using a gradient straight line function or a polynomial, it takes a function which is called logistic or sigmoid. So it returns 0 or 1, which means you have points on this axis, which have been scaled, of course, but at some point, the output goes from 0 to 1. So you only have 2 possible categories that you can assign things to. Now, this is used for classifying loan customers, to determine default risk, categorizing voters in two-party systems. You can also use it for determining spam. It's actually quite commonly used, logistic regression. But it leads on to neural networks, and I'll explain why. Now, the logistic function can be formulated as this, where this is a sigmoid function, and this is a linear set of parameters and weights. And this is known, or this is equivalent to what's called a one-layer perceptron, or a one-layer artificial neural network. In this case, the artificial neural network is so limited, it only has one node or one neuron in it. So this single perceptron can be described like this. This sums up a set of input values and weights, which you fiddle around with and alter by training. It also has this weight 0, which is called the bias, and this is to get it above some certain value that you want it to be, to regularize the equation a bit. And then it passes into this logistic function. There are different types of functions, not just sigmoid. You can use step functions, and this perceptron is a node that takes in a set of weighted inputs, applies a logistic function, and then spits out an outcome. Where if the dot product of the vector with your weights multiplied by, and your input value is x plus the bias is greater than 0, it'll return 1. Otherwise, it won't return anything. Now, this is sort of the dawn of neural networks, and I'll explain why. Frank Rosenblatt, who developed the first perceptron, he took his cue from how nature structures neurons in the brain, and this is where the term got given, really. So what you have is you have a neuron, or one or more neurons, and connections, with their own connections. They send an electrical signal and a chemical signal to what's called a synapse, and a synapse is like a gate, but it only works if the voltage is above a certain value that the receiving neutron will receive the signal. And you can see it here at this particular point. You have a marked increase in volume across the membrane, and that's a bit like having one, sorry, it's a bit like having one in an artificial neural network or artificial perceptron, and after that it drops down. But this is the sum of various inputs. So perceptrons themselves, they are quite useful, and single layers of perceptrons can be useful. They can be useful for linearly separating data sets. So an example I've used here is logical operators. They can do limited character recognition, and that's what Rosenblatt created them for originally. Here, for example, if you have an AND function, only where if you have A and B, only when A is 1 as B is 1 will you have a point which will it return 1. And you have this point here, and you can pass a line through it. Same here for A or B. You have 3 points here that return 1, and you can pass a line through it here. But this is exclusive OR, which is A or B, but not A and B. And here you can't fit a line through it. So people decided that actually perceptrons, that there were certain problems they can't solve. And we had to extend our concept of neural networks to different new layers. So we create hidden layers of perceptrons or neurons between the weighted inputs and the outputs, and these are called artificial, or these connected layer perceptrons. They're part of what we call artificial neural networks, and the use of multiple hidden layers in our neural network design is called deep learning. That's where the phrase comes from. Now, the first multi-layer neural network was designed to simulate the logical operator exclusive OR, like I described here. And then what you do is you pass in and NOR, and you pass in outputs into a NOR gate, and then you into a perceptron that acts as NOR gate, and then you get exclusive OR, and you can see how this maps into input values and biases here. So what we want to do is we want to have a model. We predict our weights in the model randomly at first, but you want to optimize them. Otherwise, the model will produce out rubbish. It won't produce out anything that looks like the output data that you have and the thing that you want to classify, you want to predict. So you need to do a process called training, which is basically optimizing to reduce errors. Now, the error, you define it as a cost function. So for linear regression, you define it to be the mean squared error. So it's essentially the same as, let me just go back to my little spreadsheet. Essentially the same as the error value that we calculated before, but then you square it, and then you sum it all, and then you divide it by the number of points. So that's how you determine that. You do that for every point in your data set. And how do you reduce the cost function? Well, one very popular way of doing it, particularly, and then pretty much the standard way of doing it for neural networks, is called gradient descent. So you start off with your coefficients or your weights, and you set them to random values, you set them to 0, and then you calculate the cost, and then you work out the gradient. So the gradient is let's say that's a space, and your cost function is shaped like a curve, and this is some local minimum, because this could be third order, fourth order polynomial and have other local minimums. But this is what you have at the moment, and you work out its gradient, and you take that away from your weight, so it goes down lower and lower and lower until you have a low cost function, the lowest cost function you can get. And this is how you optimize your model. Models being an ensemble of weights, parameters, metadata, etc. So there's two different ways of do this. One is you work out the individual cost functions, and you average them all, and you take that value away from all of the, your weights, or you do what's called stochastic gradient descent, which is mostly what they do in neural networks, and you look at each parameter, each weight, and then you calculate the cost function just for that, and then you update it, and then you update it to reduce the error. You work out the gradient just for that value, and then you do the same individually for all of your weights and all of your model. So how does this work for a perceptron linear classifier, which is the start of neural networks, if you will? What you do is you set the weights to some random value of 0. You calculate the actual output from your perceptron, and then you update the weights by taking the desired value. You work out this. You execute this equation where you have some coefficient called the learning rate R, which you don't want to be too big. You don't want to be too small. If it's too small, it'll take forever to reach a minimum, and if it's too big, it might overshoot and go back up the other end. Or so there's different. So the learning rate is something you have to figure out, and you take that from your expected value. Your output, your actual output from your expected value, and then you use that to update. Update the weight value until you reach some local minimum. Now it is just a local minimum, but that's usually, and there are ways of of extending that to possibly finding lower local minima, but the standard approach is as I've described here. So for multi-layer neural networks, we have different layers. You have to do something called back propagation, which is that you do a forward pass, i.e. you use the weights to calculate an output B. You compare the B with the desired output, the one that you're in your training data set. You calculate the error, and then you use that to go back and change the weights in your previous layers up down to your first layer. And you repeat that until you get some error that you can't improve upon or you're happy with. This is known as back propagation. This is a very, very limited way of describing it. Actually, it's very difficult to describe. You have to resort to mathematics, like second order differential equations and stuff to give it justice. But this is, a high level description of how it works. Now, let's work on different types of multilayer neural networks and their and their uses. So two-layer neural networks can be used to, say, map a road and create an abstraction of it. And this one you can put into your model, and you can pick out areas where the road is and areas of which are obstructions. You can look at the direction you want to go down in. Another example here is you can use a two-layer neural network to determine what direction someone's looking in. So you have learned weights, which are just like, messy features derived from the photographs, and you put that into your network, and then you can, and you have nodes that correspond to left, right, straight, up, and then you can predict. You can recognize which way somebody is facing. So, let's see if it's, oh, that's right. Yep. So you can have as an extension of this something called a convolutional neural network. Now, convolutional neural networks are essentially what they do is they take points in a photograph or some image, and they turn them into rather abstract features, and they compress them down to. They take them down through a process called convolution down to a single point, a single neuron, single node, which means that a particular feature can be described, as the output of a single node. And then you can sample it. You can fully connected means that every node in one layer is connected to a node in the other layer, and then you get an output, and that can recognize objects because they have something which exists in other parts of the image, or which can be defined as a feature and drilled down and spotted. That's how you can classify an image as being a robot or being a dog or a cat or something like that. So these are used in far more than image recognition. They're used in recommender systems. So Netflix, YouTube, etc. use convolutional neural networks to determine what what films you might like because of the ones you previously watched. To classify people into certain groups with certain interest in films. It's used in natural language processing to determine the structure of phrases, words, sentences, etc. Used in drugs discovery and time series forecasting, which is the bit that my first company was doing when I first learned about neural networks. So an example of a neural network is of convolutional neural network is called AlexNet, and this takes series. These are from images. These are just things that the algorithm decides as parts of the image, and then it groups. What it does is it takes each of the neurons or layers, bits of layers that correspond to these features, and then drills them down into one specific neuron. And then repeats doing that. So what you have is like greater collections of features being described by fewer and fewer parts of the next layer. And if each feature returns is summed up and returns 1, then the output returns 1, and that's known as max pooling. There's another one where it takes the average. Softmax is another type of function, a neural, I forgot what the word is, activation function. So it's a bit like a sigmoid. It's like an alternative to the sigmoid function. And then GPUs are about the hardware setup that, and when they actually interact with the feature, with the other layers to generate the features that you want. So another example of this is something allied to this, although a lot simpler, is called is the concept of autoencoders. So autoencoders, they take an image and they encode it, or an input of some description, to take up a smaller layer and then reduce noise, and then they can they make a simpler sort of image as a result, and they can and then they decode the input back into the output again. And this is useful in a number of ways. So it can take out noise, it can simplify the numbers of inputs or features, which they call dimensions. It's part of something called dimensionality reduction, and this can make for simpler models. Now, this is useful in predicting social media posts, again, image recognition, also has a place in drug discovery, and more recently and more nefariously, it's used to generate deep fakes. Now, recurrent neural networks, and this is the last one that we'll cover. These are neural networks where you can have a node or a layer that can pump the same value, the output, back in as inputs, or it can pass it into earlier layers. Now, the idea is if you map it over time, and time is this axis, it's like a linear neural network. But these are all the same node, but changing over. But the values of the change over time. And these have particular uses in speech recognition, languages, handwriting recognition, translation. You can think of them as exercising internal memory in doing this, and in fact there are particular neural networks that are thought of as emulating memory, such as LSHTMs, long short-term memories, and hot field networks that are based on this principle in some way. Now let's move away from neural networks and talk about model selection and performance. So what you do is you, if you have a model and you want to train it, usually what you do is you want to check that the output matches the expected output. So you split your training data or your data set into training data and validation data. So you typically 80% of your data is in training and 20% is set aside, or they call it holdout, just to check the output of your the model against the expected or actual data. And then if you're happy, if your model passes validation, then you test it on previously unseen data, a separate test data set. And only if you're happy, then will you be content with your model and send it off to production or use it for its desired purpose. There are other ways of doing this. One of them is called K4 cross-validation. So it's quite simple to understand. You take a data set and you cut it up into K sections. And you train on K minus one of those sections, and you validate on the final section. And then you iterate through each section and turn that into the validation section and train on all the others. And then you get all your validation errors, and then you divide it by the number of folds or sections. So you can take this down to even one individual data point, training on the rest, checking on one. This is called one in, one out. Now, for binary classification, there are other tools we can use. This is where you have two possible outcomes, i.e., an example that they have on Kaggle and they get students to work on is whether a set of passengers survived the Titanic or not, or having an illness is another example. And because they classify into only two possible outcomes, you can also do it for multiple categories, but this particular example is just two. You can create a matrix of true positives, true negatives, false negatives, and false positives with your predictor results and your actual results, or your actual output data. And this is known as a confusion matrix. So how is this used? So you can use these to create a series of metrics that data scientists use for whatever reason, for different reasons, and but the most prominent ones are called the true positive rate or the false positive rate, and you can plot these on a graph called the receiver operating characteristic curve, or a ROC curve. Now this is the false positive rate, which is here, which is the false positives divided by false positives and true negatives. And the true positive rate, which is 1 minus the false positive rate, or the true positives divided by true positives plus false negatives. And then you can, and if you have various thresholds that you model against, you can create a graph like this. Now, this is particularly important, and I'll tell you why in the next slide. So the area underneath the curve is known as the area under curve, or OROC, and it's particularly important in judging how well your model works. So if your curve looks like this, so essentially it essentially goes straight up and flattens at 1. That means that you have all your results are true positives, and none of them are false positives, and that's amazing. That means that your model is perfectly good at separating between true positives and true negatives, and there are no false positives and no false negatives. Now, if your curve looks like this, then that means for every false positive, there's a true positive, and vice versa, which means that your model is no better than random or tossing a coin at classifying, between the two categories. And if you have this, where the false positive rate is 1 and the true, and the if you have this where the false positive rate is close to the bottom, then the model's actively mislabeling all the input as the wrong category, which means that everything you see, which means that every value that you're putting in to classify is coming out as the wrong category. And that is very, very, very bad. That's just awful. So let's move on to our final section in this talk. It's about bias versus variance. And these are also ways you can evaluate models. Now, which of these look right to you? This is from regression, and this is classification. Just think about that for a second. Okay, so let's move on. Now, I'll come back to that graph in a minute, but we'll just define a few terms. Now, we have, in evaluating classification models, we have a concept called the bias-variance trade-off. Now, bias is a difference between a parameter's expected value and its actual value. So if you look here, something like this for regression has a very, very high bias. So the expected value is is the line of the graph, and the actual value looks nothing like it. Same here. You've tried to linearly fit a straight line in a classification model, and there are loads of things here in the wrong classification. So this should be red. There are loads of blues. So that's quite a high error. Now the next one is called variance, and this is the sensitivity of the model to picking up noise in the training set. And this is important because if it picks up noise in the training set, it may perform poorly in the test set or in the validation set because it's too trained for the training set and nothing else. So an example of that, a rather facetious example of this, is this. So you have a point that you have a curve that needlessly passes through exactly every point or almost every point on the graph. Now that's fine, but your test set will probably look quite different. Your validation set could be different, so it won't be able to map through all of these points there, and you can end up with a high error. Now, something more balanced is something like this, which is kind of a smooth curve that does a good job of going through most of the points. Same here for your classification. This one here tries too hard to pick up all of the red points and classify them. But these are probably outliers. They may not exist in your test set or your validation set. So something like this is probably more appropriate. And this is called high variance, and this is called high bias. Now, if the bias is too large and the model relationship between input and output is very poor, this is called underfitting. And if the variance is too large, then the noise in the training set is too prominent in your model, and therefore it may perform poorly against the test set. This is called overfitting. I mean, you want to balance between the two because sometimes reducing bias increases variance and vice versa. So you have to make a judgment about what's a suitable model, what area you're going to tolerate. So this is an example. Basically this restates what I previously said. So, underfitting, high training error, high bias, overfitting, low training error, but the test error is a lot higher, and that's called high variance. There are ways to reduce this. So for underfitting, getting more input data, running your model more. If it's KNearest Neighbor, you reduce the number of K so that it's more responsive to individual data points. If you're reducing overfitting, then you have fewer variables. You increase K, so it becomes a bit, flatter like this. And there are techniques for linear regression called L2 and ridge regression, which are mathematical terms which I won't discuss here. Now, there are other things that to think about, and this is where testers can really play a part. Over and above just statistics, prejudicial bias. So I just want to move on to the next clip and just play a video about prejudicial bias in hiring.
That I could already do a better job than Donald Trump.
Sophia, the world's first robot citizen, clearly has an opinion on President Trump. She's biased. In this case, her opinions are harmless, fun even.
I love coming to Barcelona. I would like to sneak out and explore the Gothic Quarter.
But artificial intelligence is now being used in hiring, healthcare, and the criminal justice system. If biased opinions on Trump and Spain are swapped out for race, gender, and sexuality, does AI move from helpful to harmful?
We need to make sure when we approach AI, we are doing it in a way that serves society. And that means making sure AI doesn't have bias, that we build and test it for safety.
Like most machine learning, Sophia's opinions are based on an algorithm. That algorithm is based on data.
The data that they are trained on often has biases inherent in them, and often they are replicating those biases and they are strengthening those biases. So in the criminal justice system, we've seen this in bail and sentencing decisions. We've seen this when it comes to credit risk insurance. We've seen this in job applications when women are much more likely to be rejected by AI than men.
In 2018, Amazon had to scrap its AI recruiting engine because it started showing bias against women. The technology was trained to observe patterns in resumes from a 10-year period. Most came from men, a reflection of male dominance across the tech industry.
This is also about discrimination, it's about exclusion, and this is because these technologies inbuilt in them are certain kind of biases, and these biases are a byproduct of the technical methodologies that are being used.
US lawmakers have proposed a bill, the Algorithmic Accountability Act of 2019, requiring major tech companies to detect and remove any discriminatory biases embedded in their computer models.
So that's a video that was published by Reuters on a particular case of Amazon's AI.
Well, that I could already do a better job than Donald.
Sorry about that. AI recruiting tool, which is a machine learning model that takes about 10 years of data and uses that to classify who might become the best candidate for a particular role, and then takes new hires and tries to, determine from that classification who they should bring to interview or how to rank them. So it allocates candidate scores 1 to 5. However, it suffers from biases in the data, particularly because men have dominated IT for so long. There's a historic lack of women in IT. So ways that women do to establish themselves end up being ignored or unfairly prejudiced in the rankings. So there are examples of this. This was taken from an article, HRM Online. Inclusion of the word women. So if you have women's drama club or some sort of extracurricular, then the AI hiring tool, doesn't really take that into account or takes it in view of it. Listing attendance at 1 or 2 all-female colleges. Now, if you don't have any previous Amazon employees who went to them, then women will be unfairly prejudiced against more mixed universities and colleges, where they have more men working in Amazon who used to be alumni of those places. Favoring language which is more commonly found on the CVs of men, such as power words like executed and captured, etc. The AI tool, the model, picked those up and because they have more men in their hiring practice in the past who use those words, they ended up being boosted up the rankings. And women ended up being unfairly prejudiced because they didn't include those words. So this is an area that I feel testers really ought to be able to impact upon, just along with things like ethical issues of self-driving cars, that sort of thing, just because we are not algorithms, and we can look above and beyond just statistics. Let me just move on.
Well, that I could already.
So thank you. That's the end of the talk. We'll be having a question and answer session if you're interested. So you can find me on LinkedIn at this URL here. I am on the job market if anyone's interested. Twister, you can find me at Testing Rants. These slides, you can find me at this URL, and I'll be putting this in the chat and in the description. And some resources, YouTube playlists I found particularly useful in learning machine learning. There's some great playlists. They require some maths, but they are quite comprehensive. Machine learning and deep learning by an ex-Oxford professor called Nando de Freitas. There's and some playlists with some more practical examples, actually showing coding and how you could clean data and generate models, etc. The UNSW Data Science Society. I'm a member of this society. I'm a student at UNSW, and they do some pretty good resources. And I've got the Super ML cheat sheet that I used to. I took some of the diagrams and images from. You can find that here at stanford.edu. Shervine. Thank you very much. If you have any questions, or I'll pass you back to Matt. Thank you for listening. Let me just.
Thank you so. Oh, thank you so much, Paul. That was comprehensive.
Thank you. I've really enjoyed speaking. It's the first time I've done a talk in over a year, actually, so it's quite nervy. Just to
can people ask questions verbally, or do they need to put in the chat window, Paul?
Oh, they can put it in the chat window, or they can hop online. We can only have 10 people here, but I can invite people to join this chat if they want.
Yeah.
It's using a tool called StreamYard that opens the the whole chat interface inside your browser. You don't need to install anything.
So questions via the chat, or if you want to talk directly, are both welcome.
Yep.
While we're thinking about that, I just talked about our upcoming talks that we've got. I'll be doing a talk either late March or early April on how to implement the test pyramid. I recently did a course with Janet Gregory, who's a co-writer of the Agile Tester with Crispin.
Lisa Crispin.
Lisa Crispin.
Yeah.
And her section on the test pyramid, I went, oh, wow. So I thought Sydney testers might want to hear that. Okay, questions?
Shiva's just joined the stream. Let me add Shiva. Hello, Shiva. How are you? Your sound's off. Shiva, are you there? You're not muted. You should be able to speak directly.
Yeah, Paul, can you hear me?
Yes, I can hear you fine. Thank you.
Yeah, Paul and Matt, thanks for taking time out and allowing us to know a new thing. Okay, I'm a software tester from around 6 years, but I'm looking to enhance my skills in a new area. I think knowing the machine learning, I was actually waiting for this meeting. Okay, to know more about machine learning, to how I need to start. So I'll just keep a short question here to Paul. Okay. As being a software tester, okay, a person wants to get into the ML as a testing side of it. So where I need to start, and what would be my initial kind of baby steps to start with, and what should I do?
I can tell you how I did it, and I kind of came into it fortuitously because I happened to work for a company that already did neural networks. However, there are some very good resources online that are quite academic and also quite vocational. They teach you a lot about the frameworks. I've listed a few in the last slide. It's going to be a lot of hard work. I mean, it took me a bit of math, learning a lot of maths again to be able to get as far as I had done. And I've done 2 courses at university on neural networks and worked. So it's a bit of a hard slog. However, saying that, you can actually become useful in neural networks without necessarily knowing a lot of maths or theory. If you go to Kaggle or you go to like Data Camp, there are various exercises that can take you through how to use various tools and very abstract explanations of various new machine learning topics. So like data camp, for instance, it's some of it's free and some of it isn't, sadly. There's a website called Kaggle where people they have challenges listed, and people do these sort of neural network or machine learning type challenges, where they sort of give you like an overview of the tools, and then you just practice and then get good. However, you do need a mixture of theory and practical experience using frameworks. Otherwise, it just appears like sort of magic. I'm just putting some links in the chat to some resources that already exist. The UNSW Science Society that I include in the chat's quite. I mean, they start at a level which is about the same as young people first starting computer science at university. So that you might find some use from watching some of those. Shiva, is that all right? Or
Yes, Paul. Thanks for that. And I just gone through the links which you just provided. I'll go through them. And as you suggested, okay, being in background from this electrical electronics, but having the mathematical knowledge, but it being very wide. As you suggested that I'll also go through the required prerequisites before I start with machine learning and AI. So yeah.
Well, I think you can actually start. I mean, you may not be able to get a job as a data scientist, and neither can I, really. I mean, but what you can do is at least get yourself on the page where you have some knowledge, and this is the whole point of the talk, even from watching this, where you can at least have a conversation with a data scientist, and when they mention a term, you actually understand sort of what it means.
Yeah.
Because even that is a lot higher than the vast majority of testers.
Yes, indeed. I understand few terms with the data science, but being in web and the API software tester, so this area of the machine learning would be definitely in a challenging and advanced level of the concepts which I need to look at. And being in a state of this kind of market, I thought machine learning would be a right and a kind of a start where I can pick it up. So, yeah.
Well, there is a bit of learning in terms of things like maths and computer science concepts, but people learn this all the time when they get good. So I don't think there's anything about testers that suggests that they're incapable of learning about machine learning. And if you put the effort in, I think you can get there. I mean, so many testers these days come from a computer science background, so they may have already learned some of it, or at least learned the background in terms of maths or data structures and algorithms. So you can get there. You can get there, and testers generally can get there.
Yeah, I agree with you, Paul. Thanks for that. Thanks for motivating. Yes, as I said, like being a background of electrical electronics engineer and electronics engineer, I got a chance of working also. I did my post-graduation thesis on neural networks, actually, but it's been very wild in 2012. So, so it's been very wild that I haven't touched back on that. So now there is a drastic change in the machine learning, neural network, or deep learning and everything. So there's a drastical change. So I think I need to start from scratch. So.
Oh well, you might find that you know some stuff anyway, or that you can pick things up quickly because you've had the maths background and analytical background from electrical engineering. So you can have a look at some of the resources that I posted and find that you even if you don't know much now, you can learn fast.
Sure, I'll take a look on that.
I just want to quickly thank Matt. He's had to go because he's got dinner on the table, but he did a great job of hosting. I'm usually the one who hosts, but I don't want to host and present at the same time. So he did a great job of stepping in and hosting, and I can't thank him enough. Sorry.
Thanks, Matt. Thanks, Paul.
No problems. Is there anybody else in the chat who has any questions? Let me just go back to the or anybody else who wants to hop on? Because if not, then I'll wrap up the meetup. Shiva, do you have any additional questions?
No, Paul. I'll just keep in contact with you. I just tried to take the screenshot of your LinkedIn, so I'll get in touch with you over the LinkedIn.
To be honest, I'll just take it and copy it and put it in the chat. You don't need to take a screenshot. Yeah, feel free to connect with me. Anybody who's watching, I'm always up for meeting, for connecting with people, especially, right now it does help on the job market as well. But certainly, I'm trying to connect with as many testers as people with the same interests as me. So it's all good, and I might be able to send you some more resources if I can think of some.
Sure, definitely. I'll get in touch with you, and I'm planning to start from with machine learning and everything. So I'll keep in touch with you to learn more and to get to know. Yeah.
Yep. No problems. Well, thank you very much. I'll assume by the fact there's no more questions or people join the chat that there's the people are quite satisfied, and I can sort of drop off. So thank you very much for watching. I hope you got something out of this, and it's a very large and broad area. I'm sorry I didn't include many practical examples, apart from the most basic ones regarding linear regression. I felt that you had to get to a certain level before people can understand the practical examples, and I'm planning to do talks about that later on in the coming months. So watch this space, and thank you very much, and have a great evening, everyone.